Morning. How are you today? Right. Are you ready to continue linear algebra course? All right. So just to remind you what we talked about last time. Last time we started with very basic mathematical operations on matrices and vectors. We talked about addition, subtraction, multiplication of vectors by vectors, vectors by matrices, matrices by matrices. Learned a little bit about how to solve linear equations. Haven't got too far with that, but you've seen a few methods to solve a system of linear equations, and we will not work with systems of more than 3 variables typically. We talked about a few definitions of what transpose is, what we can do with matrices, standard types of matrices like in identity matrix or diagonal matrix or triangular matrix, things of that kind. But all of that we are learning just to get to a very particular and important topic for control systems, which is topic of eigenvalues. But to get to that topic of eigenvalues, we also need to learn about additional terminology in linear algebra, which is very popular in that field, and it relates to rank of the matrix. And rank of the matrix is related to number of independent or dependent rows of columns in the matrix. So we need to learn what that dependency means. All right. So this is what we will be talking today. We will get to all of the functions that we need in that course. And pay attention that after we learn that, I will connect all of these eigenvalues to the actual control systems. Because right now it seems to be like pure math, right? So we are talking about pure mathematical things. But next lecture, I will connect all of the things that we learned today to control systems and how they relate to control systems. A little bit surprising, but you will see how it goes. All right, so we'll start with a few definitions, which are important for understanding what rank of the matrix is. First of all is span and linear combinations. So linear combination of particular vectors v1, v2, v3, up to a vector vn is just some constant times first vector plus some another constant times second vector, and so on. This is called linear combination of vectors. So this is basically weighted sum of multiple vectors. This is linear combination of vectors. And you write it like that. So you have vectors of m elements, and you have n vectors. So linear combination of n vectors, and each vector is m components, will look like that. So it's some coefficient alpha 1, which is constant number, times the first vector, plus some other constant alpha 2 times second vector, until you get to the last constant times the last vector. Any questions so far about linear combinations and what that is? You just combining vectors as weighted sum of vectors. And you get vector of the same size, dimension, right? Because you're adding just vectors, it's element by element addition. But they are scaled by particular numbers. So you multiply them by constant. So all of the values are multiplied by that constant in the vector. Then you add them together. Linear span of these vectors is all the possible linear combinations that you can make with these vectors. So I'm giving you a bunch of vectors. All of the possible linear combinations is called span of the vectors. And obviously this is infinite number of possibilities here, how you span the space with these vectors. All right, we will not talk much about span, so you can skip that part. Now, this is very important terminology. What is linear independence of multiple vectors? I'm giving you n vectors. You have some bunch of vectors. You want to identify if they are linearly independent or maybe dependent. So if you have some proportional vectors, which means that one vector is multiplication of another vector, then they are dependent. This is what it means. If you can write one of the vectors as combination, linear combination of other vectors, this means these vectors are dependent. This is practically the definition of what linear independence is. This means that you cannot write any of the vectors in your group as a linear combination of other vectors in the group. Now, mathematically, you write it the following way. So practically any coefficient alpha 1 times your first vector plus alpha 2 second vector plus and so on. So this is linear combination is equal to 0 Pay attention that this is vector of zeros. This is not number zero, right? Because some of the vectors of size m will be vector of size m. The dimensions will not change from the addition. So what happens is that this is m zeros, column of m zeros. This is if and only if all of these coefficients are zero, which means you have trivial solution and only trivial solution. This is when they are completely independent. And trivial solution always works, right? So if you put like alpha 1 equals alpha 2 alpha n, all of them are zeros, obviously this is zero, vector of zeros. So 0 times anything is 0. Is it clear why trivial solution is always correct? But we don't care about trivial solution. We are saying if you have any non-trivial solution to that thing, then it is dependent. So if you can find any coefficients where not all of the alpha are 0 for that system of equations, then the vectors are dependent. And obviously, if you can write one of the vectors as a function of all of the rest, you clearly get that. Why? Because you can move all of that side to the right side, right? And you can divide everything by alpha 1. And you'll get v1 equals to minus that thing divided by alpha 1. That's your representation. But you can go also other way around. So alpha 1 will be equal to 1, right? And then you move it to other sides. You have that non-trivial solution, which is giving you exactly what you want. So it's linearly dependent if you can write one of the vectors as a function of everything else with alpha which is not 0. Now, the requirement here is that you need actually to solve the system of equations to see if you have non-trivial solution or you don't. And we will not do that. All we will care about is to decide if they are linearly dependent or independent. We will not look like how many coefficients are non-zero or some other features that linear algebra also provides theory for, which is related to definition of rank. So rank tells you how many vectors are linearly independent out of your set. So if you have n vectors, some of them might be dependent, some of them might be independent. So how many of them are independent? Like what is the biggest group of independent vectors that you have? This is rank. And typically we are looking on these vectors as columns of the matrix. So we put them in the matrix. So this will be rank of the matrix. Now there is theorem which states that rank of the matrix is the same for columns and rows, which means number of independent rows is exactly equals to the number of independent columns. This is exactly the same thing, which means from our perspective, it doesn't matter if you put them as columns or we put them as rows, these vectors, okay? But we're typically using that as columns because I defined vector as column vector by default, right? This is just definition practically. Now, there are multiple different conditions that you can associate with full rank of the matrix. And full rank means that the number of independent vectors equal to dimension of the matrix, like all of them are independent practically, linearly independent. And full rank, especially for square matrices, is relatively easy to identify. You just compute determinant of the matrix. If determinant is not 0, then they are linearly independent. If determinant is 0 of that square matrix, then they are dependent. So this is relatively easy to identify if the matrix is full rank or you have some dependency in the vector. So you don't need to compute all of the system of equations, all of the other things to find number of independent vectors. All you need to do for square matrices at least, you just compute determinant. If it is 0, you have dependency. If it is not 0, you have no dependency. As simple as that. All right? Questions? Also, you need to pay close attention that non-square matrices do not have determinants. And this is typically mistakes that students might be doing in their homeworks and other things. You have non-square matrix, and then you need to find rank of that matrix, or if it is full rank. And people are doing like log determinants or all kind of other things. I saw all kind of things that people are trying to fit that determinant into non-square matrix. You just can't. That's not how it works. You still can do system of equations. and other ways to identify rank of the matrix, but you cannot use determinant for that. Determinant is only for square matrices by definition. Yes.
One second question. So we know that like determinant can be calculated only on the square matrices. Let us say there is a column matrix, like let us say 5 by 2. Why can't I add 3 more columns of zeros like padding and like make it into a square matrix, and I can calculate the determinant to that, right?
First of all, in any matrix where you have column zeros, it's not full rank by definition, because zeros are dependent. If you look in a linear combination with any vector which is zero vector, by definition it will be dependent, because the coefficient which multiplies that zero vector might be non-zero, and it's not trivial solution. It could be actually any number. So any number times vector of zeros is still zero. So it is dependent with any vector. So vector of zeros is dependent with any other additional subset of vectors, okay? So you cannot pad it with just zeros. More than that, vectors or matrices which are not square, their minimal dimension is their maximal possible rank, which means if you have like 5 by 2, your rank will not be higher than 2, ever. And this is why students, I saw students like trying like 2 by 2 blocks inside of that matrix, trying to fit that to see if this determinant somehow combined to whatever. But this makes no sense. This has nothing to do with rank, okay? You're doing sub-blocks of any non-square matrix, because determinant is defined only for square matrices, right? And padding will not help here. It will not tell you the rank, because the determinant of that padded matrix will always be 0 by definition of padding. With any vector of 0 in any matrix, the determinant will be 0, right? With any proportional lines or proportional columns, the determinant will be always 0. It's like having the same equation twice in the system of your equations, right? And this means that you have more variables than equations. Actually, one of the equations is just you padded it with same equation twice, right? So you do not have a single solution to the problem. Any other questions? All right. By the way, determinant not equal to 0 also means that matrix is invertible, because if you remember, we divided by determinant to compute A inverse, right? We talked a little bit about inverting the matrices. And now we get to the main topic here, motivation for eigenvalues and why they're important, why we concentrate on them. But this motivation is still not for control systems, it's just generic meaning of eigenvalues, what they are, what they mean. So here's how it goes. If you remember multiplication by matrix, we define that as some sort of transformation of space. So if you multiply a matrix by a particular vector, which is just dot in n-dimensional space, you rotate it, you scale it, you doing manipulation on that vector practically. And different vectors obviously will be manipulated differently by particular given matrix, right? So they will move somewhere in space, right? The point will move somewhere else with multiplication by the matrix. You'll get another vector of the same size. You cannot modify the dimension of the vector by multiplication by the matrix in that sense. So you get vector of the same dimension, size. Now, the question becomes, an interesting, fun question from eigenvalues is, what are the vectors which are not rotated but only scaled? Like, can you find such a vector when you multiply it by matrix, it will not move anywhere else. It will just be stretched or squeezed. That's it. So it will look in the same direction. The pointer will be in the same direction, or maybe opposite directions, like negative direction, but on the same line, on the same straight line where it was originally. That type of vectors are called eigenvectors. From German, like self vectors. They are not changing their direction at all. These are eigenvectors. And this is why they are interesting. Okay? They are interesting because they are used in multiple different domains of science and engineering. You can use it in PCA analysis, principal component analysis, which is used a lot in statistics and used in machine learning, used in multiple different algorithms. You can use it in signal analysis as well. You can use it in PageRank algorithm from Google. You know, search that was developed by Google's search algorithm, which is called PageRank. They rank the pages based on the eigenvalues and eigenvectors of different pages. They practically identified which page is the most popular or most cited in other pages. And to identify that, they used algorithm which used eigenvalues. You have that in state space control, you have that in face recognition, you have that in many different areas. And you have a lot of it also in computer vision and machine learning and communications. Like you pick your engineering area, you will find something with eigenvalues. And the reason is very simple, because this problem of what kind of vector is not changing their direction pops up in multiple different domains, in solution of differential equations, in solution of different problems in engineering. That's why it is so important to learn about eigenvalues. And even if you're not using that for control systems, you will definitely use it somewhere else. Okay, you will see them popping up in all kind of weird places, unexpected places. So it's good to know what that thing is. So here's how I mathematically define that problem. Okay, problem of eigenvalues and eigenvectors. So let's say you have some matrix, square matrix, n by n, and let's call that matrix A. And again, I'm using already terminology which might hint you a little bit on how we will be using that specifically. So I call my eigenvalues S, should remind you of some Laplace variables. Okay, we will have those eigenvalues S of that matrix A, and they need to be solving that type of matrix equation. So vector X is eigenvector, and constant S is eigenvalue that corresponds to that eigenvector. So let's see what it does. So what I'm saying is, if you take in that matrix A and multiplying it by vector X for that particular vector, which belongs to that particular matrix, okay? This is the same thing like multiplying by a constant of the same vector, which means I'm multiplying by constant vector xi, which is an eigenvector. It's the same thing like multiplying by matrix of the same vector. So matrix is practically not changing the direction, it's just multiplying by constant. You remember what is constant multiplied by vector? It's just scaling, right? It's scaling the vector, making it longer, shorter, maybe opposite direction, if it is negative. So the thing is that matrix A has typically n different eigenvalues. Sometimes they are the same, sometimes they are complex, sometimes they are real numbers, but they are n different complex or real numbers, okay? And you can find n of them by solving that thing. But it's too complicated to solve that thing to find both of them at the same time, right? You need to find both x values, which are the eigenvector, and you need to find all of the SI values. So the way to do that is the following, okay? How you actually compute the eigenvalues and eigenvectors. This is the technique. And before we go into that, I wanted to ask you a question which is stating something like, how many of you don't know how to compute eigenvalues, eigenvectors, and all of that kind of thing? And I expect that nobody will raise their hand, because this is what typically happens. So I will reformulate exactly the same question in a different way. Who can come to board and compute eigenvalues and eigenvectors now? Okay, who actually remembers how to do any of it? Raise your hand. If you I'm giving you matrix, you're computing eigenvalues, eigenvectors. Now, zero result. One maybe, approximately, okay, with help. Okay, we have one with help. Anyone else with help? Okay. All right. So let's see how we do that. And here I'm using a little bit different notation from typically you would see in the textbooks, but it's not really different, it's the same thing. I will show you how the difference, and I show you how you can convert one into another. It's very simple. So here's our equation, okay? So we'll start with the equations that we need to solve, okay? So we need to find S and we need to find X. These are the two things, and we need n of them, n times the same thing. So I'm doing some simple trick here. And this simple trick is multiplying by identity matrix here in the middle. So I'm multiplying x here by matrix I, which is ones on the main diagonal and zeros everywhere else. This identity matrix. Remember that? Square matrix. Still n by n matrix, obviously. Can I do that? Of course I can, because I times any vector or any matrix will be the same matrix or vector. So I haven't changed anything in that equation. But here is the tricky thing which many people miss. S times I is not S. You need to be extremely careful with that. Because yes, I times any vector or matrix is that vector or matrix. But I times scalar is not scalar. It's still matrix with S on the main diagonal. Okay? So it's not the same thing. So I times anything but scalar is that anything. But I times S is matrix with S's on the main diagonal. Okay, this is how it goes. So be very careful. You cannot combine that thing with that thing separately. You cannot multiply scalar by matrix and to get scalar. This would be wrong. But I times X is X. Okay, so this is correct as it is written. Now you can move that part to that side with minus sign. This is basic algebra. You can just move it to the left side. And then you can combine A and SI together because both of them are matrices of the same size, n by n. So S times I is matrix in that sense, right? And times X. And it all equals to vector of zeros, which is n by 1, practically. I don't know why I used n here. It's vector, right? So you get that type of equation, which is some matrix times X equal to 0. Equals to 0, right? Same equation. So this equation is completely equivalent to this equation. So this equation has very simple trivial solution where X equals to 0, right? So if all of the X's here are 0, any matrix multiplied by vector of zeros will be 0, very simple. But we don't care about that type of trivial solution, right? We care only about non-trivial solution. So what is the conditions that non-trivial solution exists? So you have some matrix times some vector equals to 0, and you know that X is not 0. So what should be the conditions that you actually can compute X? Okay? So this matrix should be non-invertible, because if it is invertible, that thing that you have in parentheses here, if it would be invertible, you could multiply by the same thing inverse on the left, and you multiply 0 from the left by the same inverse. So that inverse times 0 is 0. You get cancellation here of the matrix. So you have X equals to 0, which is a trivial solution. We don't care. So the only way that this will have non-trivial solution is when this matrix is singular, non-invertible. So what other condition we know about determinants of matrices, which are singular? Determinant must be equal to 0 of that matrix. So this is a condition. Determinant of A minus SI equals to 0. This is a condition when this matrix is not invertible. You cannot invert it. All right? But this is polynomial equation, because determinant of A minus SI as a function of S variable is polynomial of nth order. You'll get something like that. And pay attention that these coefficients are not elements of matrix A. They are just some free coefficients that you can compute from matrix A. When you compute the determinant, you'll get some numbers. They just incidentally having name of A. All right? But by solving that equation, you can find S, and you will have n roots of that polynomial equation, right? Because equation of nth order, degree, you have n roots, complex roots, typically. But they will come in pairs if all the coefficients are real. So you'll have conjugate numbers, which are solutions. So you'll have n solutions, which potentially could be real or complex numbers. Any questions so far? These are your eigenvalues. So you just solve that equation, find eigenvalues. Now you have eigenvalues. You can put them back one by one into that equation. And now you need just to find that x, which works here. So this becomes just system of linear equations. You can move that thing here, right? So you can actually solve that equation for a given s. So s will be a number, right? So you can solve that system of linear equations and to find x, which corresponds to that particular s. This will be your eigenvector, which is corresponding to that eigenvalue. This will be coming in pairs always, all right? So you will have m eigenvectors and n eigenvalues, and this is all you need for the eigenvalue computation, all right? We'll see a few examples now. This will be a little bit more clean. But before we get to the example, I want to define a few more things which we'll be using a lot in control systems. And we'll have same terminology, and this is where it comes from. So in linear algebra, that polynomial of determinant of Si minus A, and this is where it is different. Pay attention that here I have A minus Si, and here I have Si minus A. This is what you typically see in the textbook, Si minus A. This is called characteristic polynomial, all right, of that matrix A. Now, why that of Si minus A, like I'm defining here, is similar to A minus Si? Like what is determinant of minus matrix compared to determinant of that matrix? It could be different, okay? But the thing is that this equals to 0. So this is some constant minus or whatever coming out, but it is 0. So it doesn't really matter for us when we're solving this equation if you're multiplying everything by 0 or by some constant or by whatever, right? Because it is 0. So both are practically the same, and I could use that way around. So instead of moving that thing to the left side and to get AX minus SIX, I could get this thing to the right side and to get SIX minus AX, right? And do the same thing. It's just less convenient to have 0 on the left side equals to something on the right side, right? It's like less algebraic way, I guess. So this is more standard way that you will see in many books to define eigenvalues and eigenvectors, okay? So this is characteristic polynomial. Our method to find eigenvalues is basically to solve that equation, to find all of the s's which are solving that equation, algebraic equation. Finding these roots, putting that back here in that equation, solving system of linear equations, finding the vector xi, which is again n variables inside the vector. Moving to the next one, solving system of equations, finding all the vectors and get the entire set of vectors. Here's an example. Let's say you have 2 by 2 matrix, matrix A, 1, 2, 0, 3. If you remember, I mentioned already, kind of passing by, that for triangular matrices, eigenvalues are very easy to compute. They just sit on the main diagonal. This is upper triangular matrix, as you can see, because you have 0 here. So I don't need to compute all of that. I can tell you that eigenvalues will be 1 and 3. They just sit on the main diagonal. Okay, this is as simple as that. But I will compute them officially now, just to show the process, right? So you will see the methodology. So we have that determinant of A minus Si. So A is that matrix minus S times that matrix. So when you multiply scalar by matrix, you get here S and here S. So you will get 1 minus S times 1. So it's like 1 minus S, 0 times nothing, minus S times 0, so it's 0. 2 minus S times 0, so it's 2. 3 minus S times 1, so it's 3 minus S. It's element by element, practically, right? So now I need determinant of that thing. To remind you, determinant is the main diagonal multiplication minus the minor diagonal multiplication. So it's 1 minus S times 3 minus S minus 2 times 0, something like that, all right? So 2 times 0 cancels, you get that thing. You can flip both of them, right, to write it in more convenient way. So you'll get S minus 1 times S minus 3. equals to 0. And roots are obvious here. S equals to 1 and S equals to 3. Right? This factorization of regular second order polynomial, you get two eigenvalues, and we predicted that they will be just these values. Right? Questions about eigenvalues? All right, now we need to find eigenvectors. So for the first eigenvalue, which is 1, we just substituting here instead of S, we put in 1. Right? So you get 1, 0, 2, 3, which is A matrix times some unknown vector that we want to find, equals 1 times the same vector. And you can write that a system of linear equations like that. Pay attention that this system of equations should not be only trivial solution. It always will have infinite number of solutions. Otherwise, you made some mistake in your calculations if you do not have infinite number of solutions here. All of these equations have always infinite number of possibilities here. But let's solve them. So from the first equation, this becomes like V1 equals V1. This cancels, so 2V2 equals to 0, right? So V2 must be 0. And from the second equation, you get no information from that equation and practically 0 from that equation. So your eigenvalue might be anything here. It could be any number, whatever you want, and 0. Now, typically we like to pick numbers where the normal of the vector will be 1, or we'll talk a little bit about that, how you normalize the vectors, but doesn't really matter. You can pick any number which solves the system of equations. And same thing with the second eigenvalue. So you have eigenvalue equals to 3. So I put it here instead of 1 now, okay? And solving for another vector. So this is not the same vector. This is second eigenvector that I need to find. So when I multiply that thing by that thing, I get the first equation. Multiplying that thing by that thing, I get the second equation. Second equation, no information. Why? Because it's like 3v2 equals to 3v2. V2 might be anything, practically speaking, right? You can pick any value, and this equation will be correct for any v2. But first equation you can solve and to find that v1 equals v2. This is what you get from the first equation. So you need to pick any v2, but v1 should be exactly the same. Whatever you picked v2, pick v1 the same, because this needs to be satisfied. Okay, let's pick like 1 and 1. You can pick anything else, 5 and 5, 10 and 10, whatever you like. Okay, all of them will work. And again, why it doesn't matter which vector you choose? Because we are talking about scaling in the same direction. So it doesn't matter from where you start, just scale it in the same direction, multiply it by a constant, practically speaking. So it doesn't matter what your original size of the vector is, just scaling it. All right. So here you have two eigenvectors, which correspond to these eigenvalues.
Wait, and you said you'll always, in all of these, have an infinite number of solutions?
You always have infinite number of solutions, yes.
No, because...
So any vector which is sitting on the same line will be eigenvector. But you have orthonormal eigenvectors, which are only unique solution, which means the length of 1. So you can normalize it to length 1. If you normalize it to length 1, then they are defined as orthonormal vectors. Also pay attention to something very important, that the eigenvectors will have particular properties, and we will see these properties, but another example. This is actually a very interesting example from computer vision. People are using that particular matrix a lot in computer vision. This is called rotation matrix. Why? Because if you're taking any vector, any point in space, okay, any pixel in the image, and you multiply coordinates of that pixel by that matrix, it rotates, literally rotates around the origin, the pixel by angle theta. So it moves it, makes angle, right? Multiplying by that matrix, you can try that. Pick any coordinate, xy coordinate, multiply by that matrix with given angle. This coordinate will be moved by angle theta, counterclockwise. This is how this cool matrix works, rotation matrix. Okay, you have similar matrices for 3 dimensions, more dimensions, which is interesting. Okay, so we need to compute that characteristic polynomial, which is determinant R minus SI. This matrix, I call it R, rotation. This is what it will be. So it's cosine theta minus s minus sine theta, cosine theta minus s. Okay, so it's this element times this element minus this element times this element. You will get some trigonometry to do here. For example, cosine squared plus sine squared will be 1, if you remember trigonometric identities. Okay, so it will be simplified to that quadratic polynomial for a given constant theta. Right? Now, if you find roots of that quadratic polynomial, this is what you will get. And just to remind you, this is just quadratic polynomial. You have formula for the roots, so you can use it. We worked through that, I believe, in the second lecture or something, how to solve quadratic polynomials. All right, so you get cosine theta plus minus square root of cosine squared minus 1. So again, this is minus sine squared theta, what you see inside, like cosine squared minus 1 is minus sine squared, right? So it's always negative. And square root of something negative is j times square root of that thing, right? It's like square root of minus 1. It's complex, must be. Because that number is always at least as small as this thing. So cosine squared is always less or equal to 1, right? So something that you have inside the root is negative. So it must be j times sine of theta. So pay attention what that thing is. This is exponent as we defined by Euler theorem, right? So you get that eigenvalue of that matrix, actually two eigenvalues is e to the plus minus j theta. But what that thing is? What does it mean to multiply by e to the j theta? This is what you do, right? So when you multiply something by e to the j theta, remember these are points on unit circle, e to the j theta, like one direction or another direction. So when you have polar coordinates of e to j theta, right? And you multiply by this polar coordinates particular vector, what happens to the vector? You're just adding that angle to that vector, okay? The phase of the vector is changing by theta. That's exactly what that thing is, right? This rotation matrix. This rotates the vector by angle theta. This is why your eigenvalues are e to the j theta, right? So we showed that both directions practically. And this is the thing how to normalize the vectors, okay? So sometimes you want the vector to be having size or length of 1. So you divide in the actual vector coordinates by the size of the vector to get vector of 1. And the size is called norm. And typically you denote it like that with 2 bars on both sides. Okay, this is norm of the vector. You have multiple different norms how to compute distance, but the most typical one is Euclidean norm. And it means add all of the squares of the elements and square root of that. So square root of sum of the squares. This Euclidean distance from one point to another, if you remember. And this is distance from origin. So if you have coordinates x1, x2, x3, x4, and so on, you're just taking x1 squared plus x2 squared plus x3 squared and square root of the sum. This is Euclidean distance from the origin to that point in n-dimensional space. Generalization of any other two-dimensional, three-dimensional spaces, right? Same definition, this will be that norm. So if you're dividing by that length, you always get vector of length 1 by definition. Why is that? Because let's see. So the length of the V normalized will be length of V divided by V. This is definition of what V normalized is, right? And now you can take that thing out because this is constant. This is number, right? So you can take it out of the distance. So it will be absolute value of 1 divided by that constant times length of the vector V. But that constant is 1 divided by length of V. So length will be always by definition 1, right? So you just cancel out everything. And this type of vectors are called orthonormal vectors. They are orthogonal, and all of the eigenvectors will be orthogonal, which means dot product between them will be 0, right? And their length will be 1. These are orthonormal vectors. Orthogonal vectors are just perpendicular. So the dot product is 0, but they are not always length 1. All right? Any questions? So practically, this is all we need to know about normalization and eigenvectors and eigenvalues. But now I will go to some of the uses that we will use this for particular purposes. So we will need a little bit more terminology about diagonalization of the matrices, about similar matrices, and other types of matrices that hopefully at least you heard about some time ago, but we will use a lot of that in this course. So I'm going through all of the important topics. So any square matrix, actually not any square matrix, but some square matrices could be diagonalized, okay? If you have all of the eigenvalues different, then it could be. But if they are not different, sometimes you can and sometimes you cannot. Okay, so if you have, for example, if you two eigenvalues equal to 2, then sometimes you cannot diagonalize the matrix. And diagonalizing the matrix means that you can write it as some matrix, invertible matrix, times diagonal matrix, times inverse of the same matrix. This is diagonalization representation of the matrix. So you're decomposing that into 3 different matrices. Now, more than that, this diagonal matrix will include on the main diagonal all of the eigenvalues. You will have all of the eigenvalues sitting on the main diagonal, everything else is 0. So it's diagonal matrix, okay? This matrix will be composed of eigenvectors. So we'll put them one by one, okay? So here you have all of the eigenvectors in matrix T. Then you have all of the matrix of the eigenvalues. And this is how diagonalization will look like, okay, for that matrix A. And we will see in a moment why this is so convenient to represent matrix in that way and not in some other ways. So procedure is very simple to find diagonalization of that matrix. You're finding all of the eigenvalues, eigenvectors, putting eigenvectors in that matrix, putting eigenvalues in that matrix, done, practically. And for those of you who are in neuro area, TDT is not Tucker-Davis technologies, okay? Something else. All right, so here's one example. I'm using the same matrix for which we already computed eigenvalues, eigenvectors, and so on. So you have 2 eigenvalues, 2 eigenvectors. Your diagonal matrix will look like 1 and 3, because these are eigenvalues sitting on the main diagonal. And your T matrix will look like first vector, which is corresponding to that one here, and second vector sitting here. That's it, done. Just to check that in MATLAB that you get exactly the same thing, here is a computation. You define in T, you define in D. So T times D times T inverse will be your original matrix A. Okay, so this is the decomposition that I'm getting from this example. Any questions on the example? Or anything else? All right, so you can go actually the other way around as well. So if you have matrix D, which is matrix of your eigenvalues, you can get back to the matrix A, or from matrix A, get back to the matrix D, and this is how you do that. So you can multiply, if you have A equals to T, D, T inverse, you can multiply by T inverse from that side, by T from that side, both sides, okay? Then you get Z. So this diagonal matrix you can actually compute by having the matrix T inverse first. But you don't have to, because you know what it's supposed to be. It's supposed to be 1 and 3. You don't really need to do that ever. You know that this is what you will get. So why is that important? Why we need to learn about that representation of diagonalization? Because many functions in reality could be written as polynomial series of some kind, Taylor series. And you know that you can represent multiple different functions. In calculus, you represent them with Taylor series, where you have all kinds of powers. So it's polynomial approximation for any function. And you can get it as close as you want with more and more polynomial terms, closer to your original function. Same thing with matrices. Sometimes, like many times, you need powers of matrices, like a cubed plus 6a squared plus 35i or whatever. You need to compute some elements like that. Sometimes they are even infinite series, where you have infinite number of elements of matrices where you need to sum them, and their powers of all kinds, sizes. And here is why the TDT decomposition is very convenient for us. Let's see what it means to take some power of matrix A after that decomposition. So A equals to T, D, T inverse, right? This is what we know from that thing. And we want to compute that particular polynomial of matrix. So what happens is that any power k, any degree of k, or you call it, of that thing, you can write, like, what does it mean even? Like, this matrix, what is power of matrix? What is a to the power of k? This is a multiplied by a, multiplied by a, multiplied by a, k times, right? This is what it means, right? Because we need to define what we mean by that. Because we haven't defined power of matrix. So this is just k times you multiply that matrix by itself. So what does it mean? You multiply in that matrix, which is a times a times a times a, k times. But pay attention what happens in the middle here. So it's t inverse times t, t inverse times t, t inverse times t. All of them cancel out. All of them, just you can drop them. All of the t's in the middle. What is left is the first t, the last t inverse, and d to the power of k. Like k times t. Like you multiply d k times, right? This is what is left. So that a to the power of k is actually t times d to the power of k times t inverse. But this is a very simple thing to compute, right? Because power of diagonal matrix is just all the diagonal elements to that power. As simple as that. So for diagonal matrix, it's very simple to compute powers or any other function. You're just making that element by element on the main diagonal. That's it. That's how easy it is. So to compute that thing, this is what we need to compute, okay? And these are just powers of diagonal elements in the matrix D for a given diagonal matrix, okay? So it becomes like very easy computationally instead of computing those huge powers where you need to multiply a huge matrix A by another huge matrix A and you need to do that like 20 times. Not convenient, right? But this is a huge shortcut for us. Another question here that we will handle a lot, similarity transforms. So one of the possible similarity transforms is similarity to diagonal matrix. But let's say we want similarity transform to non-diagonal matrix, some other matrix. So matrix A and B called similar, if this is the relation. And I will explain in a minute why this relation is so important. Again, this looks almost like diagonalization of matrix B, and then A will be practically the matrix that you're looking for. But here, B is not always diagonal and A is not always diagonal. It could be any matrices A and B. I'm just looking for any transform which is invertible that I'm multiplying by a given matrix B and then multiplying that by T to get new matrix A. So if this is true, A and B will be called similar. Okay, it's just definition. It's not like I'm computing A from B. It's just definition. I'm picking some matrix T. Whatever the matrix T is, it just needs to be invertible. Okay, non-singular. And then I will find matrices similar to matrix B. And this will be just T inverse times B times T. Okay, for any chosen T. All of them will be similar. And obviously I have infinite number of possibilities for matrix T here. It has nothing to do with diagonalization now, okay? It's just absolutely any invertible matrix. So you have infinite number of similar matrices to matrix B here. Is it clear why? Because you can choose any T. For any given T and any given B, you'll get similar matrix A. That's it. So why is it so important to understand relations of similarity? And we will use a lot of that specific slide and the specific relation in control systems. We will have similar systems. They have exactly the same characteristic polynomial. Similar matrices have exactly the same det of Si minus A, which means in that case, Si minus A determinant equals Si minus B determinant. Exactly the same. So they are obviously different matrices. But characteristic polynomial, exactly the same. And I know that many of you obviously enjoy mathematical proofs, right? So I will give you one, and you'll have a few more in your homeworks, okay, just for you to enjoy. So this is simple mathematical proof why this is true. Okay, some of you might be laughing, but you will like it by the end of the course, okay? You will not have any choice. All right, so why A matrix is similar to B matrix when they're defined that way, okay? So let's see. We will compute just characteristic polynomial of matrix A, which is determinant of A minus Si, right? This is how it is defined. But A is defined as T inverse BT, so I will put it in instead of A. All right, so far? I'm trying to go slower just for you to get all the steps. Okay, so I'm replacing A with T inverse BT, which is definition of what A is, right? So this is the same thing. Now, I'm doing the same trick that I used before. I'm adding I here, so I'm multiplying SI, so you have that SI. I'm multiplying by matrix from the left and from the right by T inverse and T. So T inverse times T is just I. It's nothing, right? It's not changing anything. But this is kind of tricky thing just even to think about it. And why do I need it? Because I want to put in parentheses that part and that part somehow, okay? And I want to move out T inverse and T somehow from the parentheses. So I want to combine multiple terms that I have here. I want to combine B and SI somehow. So I'm multiplying from the left by T inverse, from the right by T. And pay attention, this is scalar, so I can take it out, right? It's just constant. You can move it anywhere in that multiplication where you want it. In linear algebra, you cannot switch the order, right, of the matrices, but you can move them inside within the same order, okay? So I also can practically get out of here, okay? So it could be SI T inverse times T, you'll get just SI, same thing, right? So I haven't changed that thing yet. This is exactly the same thing like here. But now I can take T inverse here and there out of the parentheses. And I can take T out of the parentheses here. And in the middle, I will have B minus SI. This is distributivity law of matrices that we saw before. All right. So you can just put them outside of the parentheses. But you have rule for determinants that determinant of multiplication is multiplication of determinants. Again, linear algebra. So if you have determinant of A times B times C, this is determinant of A times determinant of B times determinant of C. Okay, for square matrices, obviously. So what happens is that you can multiply determinant of T inverse times determinant of that matrix, which is B minus SI, times determinant of T. But we have also a rule for determinants. You can kind of log into the previous lecture. Determinant of inverse matrix is inverse of the determinant of the matrix, all right, for invertible matrices. So this practically cancels with this one. So this one is 1 divided by this one, so it cancels them out. And you are left with characteristic polynomial of matrix B, which is exactly what we wanted to prove. The characteristic polynomial of matrix A is exactly the characteristic polynomial of matrix B. And obviously the roots of the polynomial, which are eigenvalues of these two matrices, will be the same, because this is the same polynomial, right? Any questions? Too difficult? It's actually the end of the proof. Yeah, so all we need to know here is that they have the same polynomial, characteristic polynomial, they have the same eigenvalues. And this will be very important for us because we will use these eigenvalues a lot in this course. Okay, so you'll learn why we need it. You have a few more theorems that we will not use too much, like A is similar to A transpose, so they have exactly the same eigenvalues, for example. So if you transpose in the matrix, which is just flipping on the main diagonal, you will get exactly the same eigenvalues. You will not change eigenvalues by flipping on the main diagonal. If T consists of linearly independent eigenvectors of B, then A is diagonal, which is again almost obvious because this is exactly diagonalization problem, right? So if you're taking eigenvectors and putting that in transform matrix T, you'll get diagonal matrix. That's how we do diagonalization. And here you have a few important properties which we need to mention as well, and we will use them a lot. Some of them you will probably remember by heart after a while, at least some of them, hopefully. it will be very convenient to remember some of these things by heart because you don't want to go through all of the linear algebra every single time you're doing something for example, polynomials of second order. Instead of computing these things, you just can look at the matrix and tell the answer. Okay, you can remember that just by heart what the answer is. Very convenient just to remember it. So especially you need that thing. So characteristic polynomial of 2 by 2 matrix is very simple to compute. You don't need to go like that of Si minus A, computing all this matrix minus matrix and determinant of that matrix and simplifying algebras and like write it like that. So characteristic polynomial of second order for given matrix A is S squared, which is second order polynomial, minus trace of matrix A. To remind you, trace is sum of the elements on the diagonal. You're just adding these two values on the main diagonal, plus determinant of A. That's it. Okay, so second order characteristic polynomial is very simple. It's minus trace, first coefficient, and determinant is second coefficient. So compute determinant, which is z times z minus z times z, and trace is just z plus z. That's it. You're done. With characteristic polynomial, you have the quadratic polynomial. This also comes from these rules. Like, why do we know that? To remind you, this is coming from Vieta theorem. And this is why we learned, and I mentioned at least Vieta theorem from basic algebra, where this is minus the sum of the roots, and this is multiplication of the roots. Okay, these two coefficients. And this is a relation. So determinant is always multiplication of all of the eigenvalues. This is what determinant is. And you can think about that as scaling in each dimension. This is the like super meaning of all these eigenvalues. Okay, this is the essence of that entire theory of eigenvalues. Eigenvalues is how much you scale your space in particular direction of these eigenvalues that you have. Practically stretching the space, and by how much you stretch it is the size of eigenvalue. Okay, so if you have big eigenvalues, this means that you're stretching that space in that direction of your eigenvector corresponding to that eigenvalue a lot. Okay, if it is less than 1, then you're actually squeezing it in that direction. So you're deforming the space by these eigenvalues in these directions. Okay, so multiplication of them is determinant, and determinant, to remind you, this is the size of unit parallelogram or parallelepiped, whatever number of dimensions that you have. Okay, it's like sum of two things, and you have parallelogram. This is the area or volume or hypervolume or whatever you call it for two vectors, three vectors, or whatever number of vectors. Okay, and trace, which is diagonal elements, sum of diagonal elements, equals to sum of the eigenvalues. Okay, and this is always true for any dimension, which is very interesting properties actually of the matrix, that you have very simple connections here. Another way to identify that the matrix is not invertible, that matrix is singular. So you can identify eigenvalue just by thinking what number I need to subtract from the main diagonal, and this is that thing, right? So this is matrix A, you're subtracting value Si from the main diagonal of matrix A. This is the new matrix. What value you need to subtract from the main diagonal in the matrix A to make some of the rows proportional. If you can make some of the rows proportional by subtracting particular value from the main diagonal, this means that this is eigenvalue of that matrix. Okay, this is what it means. These are kind of tips and tricks on how to compute eigenvalues without actually computing them, without doing all of these complicated computations. You have all kinds of tricks where you can just look at the matrix and say, oh, these are eigenvalues. If it is triangular, they just sit on the main diagonal. If I can subtract some particular number and this matrix will have like proportional rows, this is eigenvalue. And so on. You have multiple different things that you can do, also like determinants and other things. All right. So any symmetric matrix is diagonalizable, and all of the eigenvalues for that matrix will be real, which is very nice. So I have a few more rules. We will not use too many of them. But the main rule here would be about S equals or not equal to 0. So if you have eigenvalue is 0 of the matrix, this matrix is not invertible. Okay, so all of the non, it's if and only if actually. So if you have 0 as eigenvalue of particular matrix, this matrix is not invertible. Okay, very important rule. And here we get to, it's a little bit messy here, but we will go through exponent of a matrix. We will actually define exponent of matrix. We will use that in the next lecture. And I will show you, based on that derivation, I will show you how it connects to actual systems poles and other things like that. This will all be connected, and this is why I'm using always the S variable instead of typical lambda variable, which people use for eigenvalues. Okay, I'm using directly S because they will practically match to the S that we used in classical controls. Okay, this will be Laplace variable in our case. So here's the thing. We define multiple different functions using Taylor polynomials, okay, Taylor series. So you can represent, for example, exponent of any x, e to the power of x, as that type of sum. This is Taylor series of exponent. This is 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and so on. It's infinite series, right? We can define the same thing for matrices, but instead of x, we will put matrix of some kind. And this could be matrix times time t. Okay, so you can get it like variable t as well. So we replace x with at to get 1 plus at plus at squared divided by 2 factorial and so on. This will be definition of what exponent of a matrix at is. All right. And what I want to show is this is related to Laplace transform of Si minus A to the inverse, like inverse matrix. And this is matrix, obviously. This will be important because, again, you already see some connections with Si minus A, which is coming to eigenvalues and connects to all of these parts, okay? I'm trying to connect multiple puzzle pieces together, and you might not see the picture yet. That's okay. If you don't see the entire picture yet, we will get to the picture, right? Here I'm building all of the puzzle pieces first. And next time we will connect all of them together, and you'll see how they all stick together somehow. This is the fun part. But you have another series which we need here. And this series is 1 divided by 1 minus x. And this is how it looks like. It's like 1 plus x squared plus x cubed, and so on, when it converges. If it is not converging, then it's not true. All right. So these are two series that we'll be using. You can think about that as 1 minus x inverse. Okay. So we can define the two matrices as well. So replacing 1 minus some matrix inverse, and 1 we're replacing with I, obviously identity matrix, minus some other matrix inverse is 1 plus that matrix squared, which means repeated twice, and so on. Okay, same thing. So let's see how we write it. This is what we'll get. So I minus C for any given matrix C inverse will be written as I plus C squared cubed, blah, blah, blah. Okay, same series. Okay, you just converting that same thing for matrices instead of numbers, functions. This will be written, as I said, like I plus at squared divided by factorial by, and so on. Now, if you make Laplace transform of something multiplied by t, it's like dividing by s. If you're looking in the tables, multiplication by t of some function in time, it's just dividing by s. So in that case, it will be step response, which is I divided by s, plus a squared divided by s squared. And I'm not going like through the actual proof from the table. Just believe me that this is how you convert that thing into Laplace domain. Right? It's element by element of each of these matrices inside. So you'll get I divided by s plus a divided by s squared and so on. And now, what that thing is, you can take 1 divided by s out of the parentheses and to get that thing. Right? So this becomes already something very similar to that thing, but c will be equal to a divided by s, and you'll have that additional element. Okay? So let's start from the other end. What is that thing? So Si minus A inverse, right? It's like 1 divided by S. I can take it out of the parentheses because this is like inverse, and this is number, right? So I can take number out of the parentheses with 1 divided by. So here I can't divide because this is number, right? What is left here? So I divided that entire thing by S and multiplied that entire thing by S. Practically, this is what I've done. So what is left is I minus A divided by S, or multiplied by 1 over S, multiplied by S inverse if you want, okay? So this is my matrix C. And here I have 1 divided by S. This is exactly the same thing, like I've got from here. So think about that in the opposite direction. It's a little bit difficult to see that with inverse Laplace transform. Put that Laplace transform on that thing, right? So Laplace transform of that exponent should be, we want to prove that this is Si minus A inverse. This is what we want to prove. Same thing, right? It's just moving Laplace transform on the left side. Laplace transform on both sides practically. Okay? That's exactly what I'm showing here. So Laplace transform of that thing, which is that thing, as we've seen just now, okay, is Si minus A inverse, which is that thing from that side. So I connected exponent of the matrix as it was defined using series to that particular thing, which is Si minus A inverse, okay, through Laplace transform, which does not look like useful for anything, but it will be eventually, all right? Believe me, it will be, okay? And you will need to wait for it. I'm just saying this is the proof, right? Another thing that we need to consider is block matrices. So sometimes you want to multiply block matrices, and block matrices is not like special kind of matrices. You can divide any matrix into blocks. They could be square blocks, rectangular blocks, whatever blocks. You just kind of cross it here, cross it there, you'll have 4 different blocks in the matrix, okay? And you can divide it in multiple different ways, depends on the dimensions of the matrix, right? You're just saying that I have all kind of multiple blocks. Sometimes you have blocks of zeros, and they called block triangular matrices like that. For block triangular matrices like that, where you have like submatrix here, submatrix here, submatrix here, and 0 here, determinant of that matrix will be just determinant of the main diagonal matrices. More than that, the eigenvalues of block triangular matrices will sit here and there. So you don't care about what matrix C is. It doesn't matter. It's not affecting your eigenvalues at all whatsoever. So eigenvalues of that matrix will be eigenvalues of A and D together. Okay, you just compute them separately. They're completely decomposed. And this also will be important for that course because we will try to decompose different parts of the system, and they will be not interdependent because you'll be able to compute their stability and other properties completely separately as subsystems of the system. You will not need the entire system to compute, right? Now, determinant of that block matrix, of generic block matrix, is always determinant of A times determinant of that thing, assuming that this matrix is invertible. You must assume it, otherwise you cannot compute it. Inverse matrix of block triangular matrices is given here. So sometimes you will use it. You just need to remember that we have formula for that, okay? And we will get back to these formulas when we need them. You just need to remember that it's much easier to work with triangular matrices where you have some block of zeros in one of the corners. Because then inverting is easier, determinants are easier, eigenvalues are sitting on the main diagonal blocks, all kind of nice properties, right? Example of computations of eigenvalues, we did already, determinants, we did already. It's just example of block matrices now, like why block matrices are so easy. And again, it's a little bit messy because I wrote a previous lecture and haven't deleted the actual text as it was coming in, but concentrate on these blocks, okay? So I'm dividing that matrix like that because I want that block of zeros here. And that's obviously not rectangular, not square block. So I divide in that matrix, separating the last row and separating the last column in that matrix, and I get 4 blocks. 1 block, another block, 3rd block, 4th block, okay? So to compute determinant, all I need is determinant of that thing times determinant of that thing, because it's triangular, block triangular matrix now. So this will be determinant of A, which is that matrix. This is matrix B, C, and D. See, draw this number here. So it will be 9 times 3 minus 1 times 8, and times 3, which is determinant of scalar, is same number. Okay, you will get 105. To invert it, I'm using that rule. Okay, so it's A inverse here, D inverse block here, and here is that computational thing that I need to compute. So it's A inverse here, D inverse here, and that formula here. So I'm computing inverse of that matrix, which is 2 by 2. We know the formula for that. Hopefully you need to remember it. Again, you don't want to kind of go to formulas every single time you need to invert 2 by 2 matrix. Just try to memorize it. It's much easier and faster to remember it. It's 1 divided by determinant, flipping the main diagonal, minuses on the secondary diagonal. This is the inverse of the matrix. Then you have block of zeros here, which is again 0, 0 here. 1/3, which is 1 divided by 3, inverse of that matrix. And then I compute that kind of thing. You get some numbers here. And this is the final matrix that you have for inverse. All right. For eigenvalues, you're doing the same thing. These are eigenvalues of that matrix and eigenvalues of 3. So you already know that one of the eigenvalues will be 3. Very easy, right? Sitting on the main diagonal. And you need just eigenvalues of that 2 by 2 matrix instead of 3 by 3 matrix. Easier than 3 by 3 polynomial solving, right? Any questions so far? This is just example of how you can use block matrices to simplify your life a little bit if you have some blocks of zeros somewhere. And the last thing that we'll be talking today is about misconceptions on linear algebra. And this is a very critical topic because you are used to do all kinds of algebraic operations. And when you're doing them, you automatically canceling different things, switching different things, changing order of different things. And you cannot do that in linear algebra, unfortunately, because this is not correct thing to do. And I mentioned some of the things already, but I will repeat them again and add some new things. So first thing, that if you have AC equals to BC, you cannot cancel C. So A is not equal to B in that case at all. Typically not. It could be, but typically not. Here's one example. Like you have A times C, and this is B times same matrix C, right? So if you cancel C, A definitely not equal to B because you see I switched elements here. So A is not equal to B at all. But multiplication is equal. Both matrices have multiplication, which is same multiplication. Okay, so this is correct, but this is not. So be careful with canceling stuff. And the reason is that C is not invertible. If C would be invertible, then you can do it. Okay, but C is not. You have column of zeros. Another thing, if A equal to B, then AC equals to CB. Not at all. This is not correct. Again, this is matrix inverse. Never write something divided by matrix. It makes no sense. This is inverse matrix, which might or might not exist even. Okay, so you cannot just divide by a matrix. So there is no meaning to that. And this is funny one because if you learn Cayley-Hamilton theorem, which states that any matrix is a solution of its own characteristic polynomial, which means if you have characteristic polynomial of a matrix, and instead of S, you put in matrix A, you get zero matrix. Always, this is Cayley-Hamilton theorem, okay? So matrix is the root of its own characteristic polynomial, always, right? This is like, you have entire theory. And people try to prove it in very simple way. They just say, well, this is my characteristic polynomial, which is that of Si minus A, right? So isn't that obvious that I put A instead of S? So it's A times I is A, so A minus A is 0, and the determinant of zero matrix is 0, right? Isn't that like trivial thing, right? Done. No, okay? This is not how you prove it. This is incorrect. Again, this is the same trick that I showed you already in this lecture. S times I is not the same thing like A times I, and S times I is not S. It's matrix where you have S's sitting on the main diagonal. You cannot just replace that by matrix A because you cannot see these matrices in the main diagonal. This will not even fit the dimensions, right? It's something else. So you need to go, like the proof of that theorem is very complicated, actually. It's like 1 page of derivations to prove that this is correct. Okay, Hamilton, okay? It's not that simple. So be careful when you're putting matrices instead of scalars of some kind. You can do that. All right? Any questions? Yes.
So, in the similarity transforms, so we thought that like two matrices are similar if they have same eigenvalues, but they are not same.
They are not same.
See, so I want to ask you, what is the use of it? If I came to know that like two matrices are similar, but like they are not same, how is it serving? Like,
All
where
right,
is it
so they are not the same, but they describe the same system in our case. So what we will see that you have multiple possible implementations of the same system, and different implementations will have different properties, but they will have all other properties the same, which means you will be having flexibility in how to implement your system, preserving stability, preserving particular performance characteristics, preserving all kinds of other things, but not keeping some other properties. This is what we want. We want flexibility here. And this is why we will talk about similar systems. So they will be not exactly the same system, but they will be equivalent in multiple different ways, like in terms of stability, in terms of like settling time, in terms of overshoot, in terms of all the performance characteristics, right? Because they have same eigenvalues, same characteristic polynomial. So they practically will have the same poles, okay? But having the same poles does not mean that this is exactly like everything else is exactly the same. The implementation will be different, right? But we'll talk about that more later, right? Any other questions? All right, thank you.